we have talked about three-dimensional equilibrium and needing to satisfy all 6 equations of equilibrium, some of the forces in the x, y, and z, and then some of the moments about each of the x, y, and z axes. We've talked about the scalar approach on how to solve this in several ways, and now we're going to talk about the vector way. This is the cross product approach, and here we'll have to define each applied force. Every force that is applied there, we'll define it in Cartesian. Then we're going to pick a point, any point really, it could be on or off the body, and then find the moment caused by that force. For example, this could be the moment caused by a particular force. This could be the moment caused by another force. They're each going to have I, J, and K components, and then we're going to sum up all of the I's, which will be the moment about the x-axis, and sum up all the J's and then all the K's. Every one of these problems will have reactions to satisfy as well, and that's kind of where the point is. So there are several types of supports that we're going to consider. First is going to be the fixed support. You can see how that pipe is screwed into the wall. It has no ability to rotate in any of the 3 axes, and so that will be a fixed support type of analysis. This one is a pin. This one is free to rotate in this direction, but is not free to rotate in either of the x and the z directions. And this is the ball and socket. This has got free rotation in all 3 directions, however it resists force in all 3 directions. And there's lots of pictures in the book. This is another picture of perhaps a pair of pins, which would work. This standard looks more like a ball and socket. This one looks more like a fixed support. Most of the time you should be able to understand by observation what kind of support it is, but if it's unclear, or if I think it's unclear, I'll probably put that on the problem as you try to define it. Alright, well, let's look at a couple of problems here. This first problem is a fixed support problem. It is this pipe. It is sticking in the wall. It's subjected to 3 forces, and we're going to try to find out the reaction at that support. And here's our process. First of all, identify the type of support. In this case, I'm declaring that to be a fixed support. We're going to draw a 3-dimensional free body diagram, express all the forces as Cartesian, and then find the required R vectors from the point that we care about to those forces, perform cross products, combine I's, J's, and K's, and then sum all the forces and solve for the unknowns. Alright, first thing we're going to do is draw a 3-dimensional free body diagram. In this case, let's draw the axes. I've already sketched out this in our picture here, but we're going to call this the x, y, and z axes, right, like this. X, y, and z. Let's draw the reactions. Well, let's draw the reactions first. In this case, I'm going to say that there's going to be an OX, an OZ, and I'm going to draw the OY pointing in like this. That's sometimes a little easier to draw it out there, and you'll maybe see why it gets a little bit busy here. We know that this is a fixed support, so there's also going to be a reaction here, a moment about Z, a moment about Y, and a moment about X. Now it's important to draw those moment vectors in the correct way. In other words, if I were to draw this X vector pointing like this, that would be a negative X moment, and that's incorrect. You need to draw it so that by the right-hand rule, you put your fingers here, your thumb would be pointing in that direction, and draw it as a positive moment reaction. That's the correct way we want to do that. Alright, so we have the reactions drawn. Let's draw the forces, or let's examine the forces. The forces are, they got 320 and a 240 going through that point, and a 200 going through this way as well. Well, clearly these two go through the same point, and it may be obvious, but it may not be, that this one also goes through that point by transmissibility. So we can actually use the resultant of these 3 forces to our advantage. So I'm just going to write the resultant down. The resultant here is equal to 3, well, let's do the I direction first. That'd be 200 in the I direction. plus 320 in the j direction minus 240 in the k direction. And I'm just going to put that r vector right here. And I don't know where it's at, something, I'll just kind of draw it in here. It's probably, yeah, I don't know which way it's going. It's hard to know. I'm just going to draw it something like that. Okay, what we want to do is now define an r vector from the point that we care about, which is the point of support, to any place on the line of action. And again, if there's only one point where the force is attached to the body, then there's only one obvious line of action. So I'm going to draw that right here. I'm going to call this my r vector. And we can look at the dimensions on the picture to find out what that r vector is. And it looks like it is -2 in the I direction and positive 6 in the j direction. So that's going to be 2I minus 6j. Okay. Now let's write the equations of equilibrium. I'm going to write one equation of equilibrium so that you can see how this is going. I really care about the moment about O. So the moment about O is a three-directional thing, is going to be the reaction in the x direction plus the reaction in the y direction plus the reaction in the z direction plus r cross f of each force. Okay, so let's go ahead and just put those in there. Moment about x, which is unknown. Moment about y, which is unknown. Moment about z, which is unknown. I do have an r, and we're going to take that I, j, and k. Let's go ahead and push that up there now. We have an r vector of 2, minus 6, and 0, and a force vector of 200, 320, and negative 240. Okay, let's keep on going. I'm going to say that that is going to be equal to mx plus my plus mz plus, and then if we do our cross product, you can see that this is negative 1440 in the I direction, negative 480 in the j direction, negative 1840 in the k direction. Now that is my total moment about O. And now we combine i's and j's. I's, j's, and k's. So let's do the i's first. Here I have mx. And there. So I'm going to say that i's is going to be mx minus 1440 equals 0. And we can see that mx is equal to 1440. Now, this is in pound-feet. Now, here's an important thing to understand. What I've drawn here is the reactions. What I've calculated here is the moment. The total and so when I ask the question, what's the moment about O? Is a different question than what's the reaction about O. It's basically the inverse. And here you can see the moment about O is that, and this is the reaction about O, and those have to be equal. I mean, those have to add those two together to get 0, and therefore we get the moment is actually a positive number, even though the reaction is a negative number. And that's what you should be looking for when you're solving these things, is finding the reaction, not simply the moment. So let's go ahead and do the j's as well. We got my minus 480, and so we got my is equal to 480, and for the k's, we got these are little arrows here. M in the z-axis minus 1840 equals 0, so mz is equal to 1840. All right, so I have solved for all three of the moment's reactions about point O. Now, what about the forces? The forces in this very simple example are also going to be in the same way. We're comfortable, I think, finding reactions to forces. This is a little bit different when we're finding reactions to moments. But if I do sum of the forces in the x is equal to 0, I've got OX here. And then I have a reaction here, or a force, have to be equal to 0, so I'll say OX plus 200 equals 0. So clearly OX is equal to, let me do this over here, O in the x direction is equal to negative 200, and that's pounds. Sum of the forces in the y. So here I've got OY, I've drawn it as positive, and plus 320 equals 0, so OY is equal to negative 320. And sum of the forces in the z is equal to OZ minus 240, so O equals 0, so I'm running out of room here, so OZ is equal to positive 240 pounds. Okay, so I think you've got the process here. This is kind of how the way, or the way that you do it. Sum the moments about a point using the cross product, and then define and then sum the forces in all three directions, and you should be able to get to the solution answers here. All right, let's do this other one. Here I have a different pipe. We're going to try this again with using R cross F. And what have I got? This is the same kind of fixed support. And I'm going to go quickly through this so that you can kind of see how to do it. But here I have, let me draw the free body diagram over here, and then we'll resume it. All right, I've completed the free body diagram. Note that there's force reactions in all three directions, and there's moment reactions in all three directions. And like before, we have to make sure we draw those properly. Now let's find let's look at the force vectors. Here I have this 150 applied here in the negative k direction, so that's that one. What is the r vector that makes sense to that? Well, I think that's pretty obvious, but I'm just going to draw it right here from the point that we care about. I'm going to call that r1, and that's going to be equal to 2j, which I've done there. Then we have this other force down here is 200 in the j direction. What's the r vector here? Well, again, we can have to do a little more work here, but r2 is defined there, and here I've put it out there for you. Then all we have to do is do two cross products. When I have two forces, I do two cross products, and those are all equal to the moment reactions equal to 0. So here's the moment about A. I got a cross product of the one, cross product of the second one, and then the three reactions. I get it all written together, and then I sum the I's, the J's, and the K's, and you can see what my reactions are going to be. To find the forces, then I have to do sum of the forces. And sometimes you have to do it back and forth. In these two cases that I've given you, I should have moved that up. Here's the I's and the J's and the K's. Again, some of the times the forces are easy to see, and sometimes they're not. In this case, the forces are very easy to see, that there's going to be reaction in the z direction, which counteracts that, and reaction in the I direction, which counteracts that. And there shouldn't be any forces in the x direction because there are no applied forces. All right, well, I hope that is sufficient, and we're going to continue this with the next type of support.